Hello guys, welcome back again to Exclusive Tutorial, and today we are going to be talking about current electricity. Now, the part of current electricity we'll be taking today is actually the molecular aspect, okay? How electrons interact with each other and how they form current. Now, let's say we have a conductor like this. Conductors are actually cylindrical in shape. So if you view them molecularly, we will see something like this, okay? So this is just an enlarged illustration of a conductor. Now, these conductors have what we call atoms. And atoms have valence electrons. These electrons do not stay in a particular place. They actually move randomly along the conductor. They move with velocity that hits each electron and also other atoms. Now, this velocity is what we call the terminal velocity. The terminal velocity of the electrons. What we want to do is apply a particular force, which we call an EMF, that will help to move these electrons in a particular direction, producing what we call current. Now, let's say N is equal to the number of electrons present in the volume of this cylinder, which forms the wire. Example, a copper wire. If N is equal to the number of electrons or atoms per unit volume, I can simply say that the number of electrons will be equal to N times V. Now, let's consider a fraction of this conductor. A fraction. And this part has an area A. Okay? And a small distance, dx. Volume is equal to area times length, or we can simply replace it with dx. Since it's a small fraction, I will have number of atoms is equal to N times the volume is area times dx. Now, if you recall, current is the number of electrons or charges moving through a particular conductor in a unit time. Current is equal to charge over time. From here, I is equal to, this formula is only true when we are having a unit charge. Now, what if we are having multiple charges in the conductor? Example, N0. I will have to multiply by the number of charges divided by the time. Now, you call again. N0, which represents the number of charges, is equal to small letter n times a times change in x. Therefore, I will have I is equal to n times a times dx divided by t. N times a times dx divided by t times q. Remember, q represents the charge. I can now have I is equal to, from here, we can see delta x over t. Delta x is distance, t is time. Now, this distance is also length, which is a fraction of the conductor. And recall, the x over t is equal to velocity. Therefore, I will have I is equal to na times v with a subscript of t times q. There is a reason why I actually put v with a subscript of t. This v with a subscript of t represents what we call the velocity. Okay, v with a subscript of t rather. The velocity. And this velocity is not just like the terminal velocity. It is the drift velocity. It is the drift velocity. Now, this is the velocity or the maximum velocity in which these electrons will actually attain by the time they start moving in a single direction along a conductor. It could be towards this direction or towards this direction. But remember, there is always something which will cause the electron to move in that direction. Remember Newton's law. Okay, that force is what we call the electromotive force. So now I can say I is equal to na, just velocity times q. Now, what we are actually dealing with here are electrons. Okay, electrons, they have a charge. They have a charge of minus 1.602 times 10 to the power minus 19 coulombs. Okay, electrons have charges of minus 1.602 to the power minus 19 coulombs. Since on conductors, it is electrons that causes current to flow through it. I can replace q with e, and therefore I will have I equals na times drift velocity times e, where e is the charge of the electron, n is the number of electrons per unit volume, d is the drift velocity, a is the area, and I is the current. This is a general formula for calculating current. Remember, current is measured in ampere. This will later be talked about in our future videos. Now, from this equation again, I want to do something. Let's divide both sides by the area and see what we are going to obtain. If I divide both sides by the area, I will obtain current per unit area, which is I over A, equals NVDE. Remember, V remains the drift velocity, N, number of atoms per unit volumes or number of electrons per unit volume, and E is the charge of the electron. Now, this guy here, which is I over E, is actually a constant. It is a constant, and it is given as J. Let's represent it as J. Of course, you can use any symbol, but in this case, let's represent it as J. J is equal to I over A, where I is the current and A is the what now? It's the area. I over A is a constant which we just represented as J. And what do we call this guy? It is called the current density. I over A is called the current density. So current density is actually the amount of current in which we have in a unit area for a particular conductor. Let's now substitute. I have J is equal to NVDE. This is a very useful formula for calculating current density. Recall again, N is the number of atoms or electrons per unit volume, VD is the drift velocity, and E is the charge of the electron. Now, through experiments and observation, we can actually see that in a particular conductor, remember there are electrons inside of this conductor from static electricity, and these electrons actually create what we call an electric field. Remember, E represents the strength or the magnitude of an electric field. Now, these guys actually create electric fields, and from observation we have seen that this guy here, which is the current density, and it is measured in amperes per meter square. Current density measured in amperes per meter square in a particular conductor. This same conductor is what we are having. That J is directly proportional to the electric field intensity, where J is the current density. Now, bringing in a constant. If we bring in a constant, I will have J is equal to E. In this case, I represented the constant as sigma. Okay? So current density is equal to sigma times E, where they have their respective meanings. E is the electric field intensity. Electric field intensity. And J represents the current density. Now, what about this constant? This constant has its own name, and it is called the conductivity. Of a particular metal. Now, this conductivity measures how well current can flow in a particular conductor or a metal, which means the more the conductivity of that metal, the more that metal tends to conduct electricity. Now, let's make some other derivations. Recall again, current density is equal to I over A. Number of current we have in a unit area. Current density is I over A. I can now substitute, and I will have I over A is equal to sigma, but this electric field intensity, remember it has its own name. Electric field intensity is also called electric potential gradient. Electric field intensity is called electric potential gradient. This is because it is the ratio of electric potential to a unit length. E is equal to V over L, electric potential gradient. Let's now substitute. If we substitute, I will have V over L. So I over A equals sigma V over L. Now from here, this guy in which we call conductivity, it is also what we call the reciprocal of resistivity. Okay? Conductivity is equal to the reciprocal of resistivity. Resistivity is represented as rho. This guy here that looks like a P. It is actually a Greek symbol, okay, called rho. This guy is called resistivity, and it's the reciprocal of what now? Conductivity. Resistivity actually measures your opposition to the flow of current, which means the higher the resistivity, the less it is for a conductor to conduct current or electricity. Let's now substitute. I will have I over A is equal to V divided by rho times L. Now, I want to make V over I subject formula. That is the dependent variable. Let's make it the dependent variable. If I cross multiply and do the math, I will have V over I is equal to rho L over A. V over I equals rho L over A. Okay? Now, this guy here, V over I, it is also a constant. What do we call this constant? V over I is called the resistance of a conductor. And mind you, just the same way conductivity is the reciprocal of resistivity, resistance is the reciprocal of conductance. Okay, conductance is the reciprocal of resistance, any one you want. Now, V over I is also a constant called resistance. So I can substitute and I will have resistance is equal to rho L over A. This is a very important formula. Now, this formula is actually applied in most of the machines and it has a very vast application. Resistance is equal to rho L over A. Resistance is equal to rho L over A. Now, how does this work? How does that formula work? How do we even make use of it? This guy here is the resistance. This one is the area. This guy is a constant. And L is the length of the conductor. Now, you can see that I just said this guy is a constant. So, if I take out this guy, I can say resistance is directly proportional to the length and inversely proportional to the area. Which means, for a particular conductor, the more the length, the more the resistance. For that particular conductor, the more the area, the less its resistance. Okay? Now, look at a very good example. Let's say we are having two straight wires of 10 meters each, of length 10 meters, and I apply a particular force, let's say an electromotive force or a potential difference at this point, which we'll be talking about sooner or later. Okay? Now, if I have a bulb here, when I apply a potential difference across this circuit you are seeing, the bulb will become lit. But you observe a difference in these two circuits. This other circuit has a length of 20 meters of each wires, and there is a potential difference here, and there is a bulb here as well. Okay? Now, this one which has a longer wire, if I apply the same EMF, you will observe that the brightness of this first bulb will be more than the brightness of the second bulb. This is because the length of the conductor has actually increased. Remember, resistance is equal to L over A. The smaller the length, the smaller the resistance. And the greater the length, the greater the resistance for a particular conductor. Now, let's talk about the area. We just proved that the resistance of a particular conductor is dependent on the length and the area. Okay? Resistance of a conductor depends on the length and the area. Where this guy is called the resistivity. Now, let's see how this length and area actually affects resistance in real life and what are the applications. Now, if for example we have two conductors, let's say two copper wires of like 10 meters each, and we apply an electromotive force or a potential difference at this end and connect a bulb to this other end. When the bulb is lit, we observe the brightness of the particular bulb. What if we choose to extend these wires by 10 meters each, making them 20 meters? Okay, this is the EMF, and we are having the same bulb. You observe that the brightness of the first bulb will be far better than the brightness of the other bulb. This is because the conductors has increased in its length. Resistance has increased because the length has increased. Same thing applies to the area. Okay, now resistance is actually measured in what we call ohms. It is measured in what we call what now? Ohms. And the conductance, because R is 1 over C, the conductance is the reciprocal of resistance. So the unit becomes 1 over ohms. And this can be written as per ohm, or we simply call it from the ending to the beginning. And that will give us MHO, which we pronounce as the mole. Okay? Now, also, we said V over I is a constant. V over I is a constant, and I call this R, which I represented as the resistance. If I cross multiply, I will have V is equal to IR. V is equal to IR. This formula is a very popular formula in electricity, and it is in accordance to a man named Ohm. Okay? A man named Ohm. Let's now talk about the law which this guy named Ohm gave. Now, this guy is actually saying that whenever we apply a potential difference V across the terminals of a conductor, it is directly proportional to the current passes through it, provided certain things are kept constant. Example of what we need to keep constant is the temperature. Is the temperature of the conductor. This simply means that resistance actually varies with temperatures of what now? Of conductors. V is equal to IR. And mind you, not all materials obey this law. Certain materials that obey this law are what we call conductors or ohmic conductors. Example include silver. Example, copper, iron. These are some popular metals that obey this law. What about materials or substances that do not obey this law? They are called non-ohmic materials. An example includes electrolytes. Another good example is a valve or a diode. Okay, basically semiconductors or metals. These guys do not obey Ohm's law.
Okay, now let's take an example on the previous formulas we've derived and the explanations we took. In this case, we're having a copper wire of cross-sectional area 3 times 10 to the power of minus 6 meters squared carries a current of 10 amperes. Assuming that each copper atoms contribute 1 free electron to the metal, find the drift velocity of the electrons in this wire. Density of copper was given as 8.95 gram per centimeter cube, and Avogadro's number is 6.02 times 10 to the power of 23 electrons per mole. Atomic mass of copper was also given as 63.5 gram per mole, while the charge of an electron is 1.6 times 10 to the power minus 19 coulombs. Now, we've derived this formula on the board initially. I is equal to NEVA. Remember, I is the current, E is the charge of an electron, V is the volume or drift velocity, and A is the area, while N is the number of atoms or electrons per unit volume. Okay, N is equal to the number of atoms per unit volume. Now, we are given the current and V is the drift velocity. If I make V a subject formula, I will have V is equal to I divided by NEA. Where V, I'm putting a little subscript which indicates that this guy is actually for drift velocity. Now, we are given the current. We are given a current of 10 amperes and a charge of 1.6 times 10 to the power of minus 19 coulombs, since the charge is actually an electron. Now, another thing we are given again is the area. Area is equal to 3 times 10 to the power of minus 6 meter squared. This is the area. And for N, remember N is number of atoms per unit volume. We are not given volume of the copper. First of all, number of atoms is equal to Avogadro's number, and that was given on the board as 6.02 times 10 to the power of 23 atoms. Remember N naught, represents the number of electrons or number of atoms. Now, the reason why in this case the N naught represents the number of electrons also is actually because of a statement that was made in the question. They also said, assuming that each copper atom contributes one free electron, which means a particular atom gives one free electron to produce the current. And it also tells us that the number of atoms present there will indicate the number of electrons, since one gave one free electron. So assuming it was one atom that gave 2 electrons each, we would have said 6.02 times 10 to the power minus 3 will give how many electrons in total? Okay. Now, let us obtain the volume. How do we obtain the volume? We are given the density of copper. Density of copper as 8.95 gram per cm cube, and we are also given the mass of copper as 63.5 gram per moles. Okay, 63.5 gram per moles. Now, let's obtain the volume. Recall that density is equal to mass over volume. So volume is equal to mass over density. The mass is given as 63.5 divided by the density. The density is given as 8.95 gram per cm cube. Okay, 63.5 divided by 8.95 gram per cm cube. Now, let's divide these two guys. 63.5 divided by 8.95, and that will give us a value of 7.095 approximately to 3 decimal places. Okay, this is the volume to 3 decimal places. Now, what will actually be the unit of the volume? The mass of copper was actually in grams. The volume of copper was actually in gram per cm cube, which means the volume will be in centimeter cube. Okay, the volume will be in centimeter cube. Let's now take the ratio of this guy and this guy to find the number of atoms. Number of atoms, which is N naught over V, is equal to 6.02 times 10 to the power of 23 divided by the volume is 7.095. N is equal to 6.02 times 10 to the power of 23 divided by 7.095. Now, mind you, this guy is in centimeter. Okay, now let's divide. I will have 6.02 times 10 to the power of 23 divided by 7.095. Now, we got a value of 848.48 times 10 to the power of 20 times 10 to the power of 20 per centimeter cube. Okay, this is actually the number of atoms present in 1 cm cube of volume. Let's convert to meter because we are asked to calculate drift velocity and our answer should be in meters per second. Let's convert to meter. Now we are having N is equal to 848.48 times 10 to the power of 20 divided by 1 cm cube. Now, when we are converting from centimeter to meter, we multiply by 10 to the power of minus 2. But since we are having meter cube, we are going to multiply by 10 to the power of minus 2 3 times. Therefore, I will have 848.48 times 10 to the power of 20 divided by 10 to the power of minus 6 meter cube. This is because 10 to the power of minus 2 times 10 to the power of minus 2 into 3 places will give you 10 to the power of minus 6. Okay, and then we are going to have N as 848.48 times 10 to the power of, when this guy goes up, we have 10 to the power of 26. Okay, per meter cube. Now, what we want to do is calculate the current, the drift velocity. Drift velocity initially is given as I divided by NEA. where n is the number of atoms per volume, E remains the charge of the electron, and A is the area. So I will have drift velocity is equal to, the current was given in the question as 10 amperes. 10 amperes divided by n, which we just solved for, is 848.48 times 10 to the power of 26 times 10 to the power of 26 times E is the charge of an electron, 1.6 times 10 to the power of minus 19, and then we multiply by the area. The area was given as 3 times 10 to the power of minus 6. 3 times 10 to the power of minus 6. Now from here, we are going to solve everything using our calculator. So we are having 10 divided by 848.48 times 10 to the power of 26 times 1.6 times 10 to the power of minus 19 multiplied by 3 times 10 to the power of minus 6, and that will give us 0.000245. Now let's put this guy in standard form. If we write it in standard form, the drift velocity 1, 2, 3, 4. The drift velocity becomes 2.45 times 10 to the power of minus 4 meters per second. Okay, so that's the answer, and that is how we solve questions like this.
Learning online haven't been more fun. Exquisite Online Tutorials is a household name when it comes to academic excellence in online tutoring of 100 level students, 200 level students and college entrance examination candidates. With the power of artificial intelligence and human studies, Exquisite Online Tutorials have been able to interact with the intelligence of students worldwide, making the good ones better and even the better ones best. Just like Science Bob, Exquisite Tutorials has a great faculty of erudite tutors that inject knowledge, whether science or business management, to the cerebrum of her students. QTME lectures and other college entrance examination lectures are going on as well. Do you still need a physical tutor? No. Exquisite Tutorials got you. Please subscribe to our YouTube channel and follow us on Twitter and Facebook.